Hello Math 2413 students, let's begin Lesson 11, Antiderivatives, or also known as indefinite integrals. So far we had been studying differential calculus, that is, those related to taking derivatives and the derivatives and some more derivatives. Now let's go backward. We start from a certain function f of x, more precisely speaking, lowercase f of x, which we call the integrand. And let's find another function, capital F of x, whose derivative is the original f of x. As you see here, capital F prime of x is lowercase f of x. Such a function, capital F of x, is called an antiderivative of this original function, lowercase f of x, and we use this notation. And oh boy, this is intimidating. Let's try to make some sense out of it. We read it like this. This capital F of x is the integral f of x dx. We read it like this. Now in this sentence, the verb of this sentence is the equality sign here, and that corresponds to the verb here, is. And then this symbol here is called the integral symbol, and that corresponds to this, of course. And then we have the content here, the integrand, and then we close it with dx. Some people write as the integral of f of x like this, but I like it without this of. The reason? I regard this integral symbol as the opener, like opening a bracket, and dx is a closer, closing a bracket. So if you open, you have to close it. Therefore, this dx is very, very important. Actually, it is extremely, extremely, extremely important. If you forget to write this dx, that's going to be -1 for each mistake, and that can add up. The worst I've ever had is -13 in a single exam, and that's enough to knock you off all the way from A to C or B to D. After that experience, I'm giving a cap, no more than -10, but -10 in a single exam, just for these kind of little mistake, that's really humongous. They can add up. Make sure you don't make that kind of stupid mistakes. Let's come back to this expression here. The left-hand side, capital F of x, that function is an antiderivative of f of x. And this right-hand side expression here, that's the indefinite integral expression. So antiderivative, the left-hand side, and indefinite integral, the right-hand side, they mean the same thing. Even though technically they are a little bit different, but hey, look at this. They're equal. They're the same. So we're going to regard those two are the same. Antiderivatives, indefinite integrals. One more thing about antiderivatives before moving on to real exercises. Antiderivatives are not unique. There are multiple antiderivatives for a single function. Actually, there are infinitely many. Look at this expression. Let's begin with a function 2x and antiderivative function x squared. Please check, take the derivative of x squared, and do you actually get 2x? Yes. But so does x squared plus 1, or x squared minus 1 over square root of 17. No matter what constant I have here, that's going to disappear when you take the derivative. So we have an arbitrary constant plus c popping up whenever you find out an antiderivative function. So this x squared is actually an antiderivative, not the antiderivative, because there are infinitely many antiderivatives, and this x squared function is just one of them. And if you want to find everything, then you need this plus c. But unlike this dx, which I take off 1 point for each mistake, this plus c, I don't usually take off any point. Now, of course, if I go over to a little higher level course like differential equation or something, then of course this plus c does matter. But at this level, not very much. That's just me, as a matter of fact. There are some other instructors who do like to take some point out for here. So it is better to have this plus c all the time. Alright, so much for theory, and let's talk about some practical rules to calculate. First, the constant rule. The derivative of c is 0, any constant becomes 0, so antiderivative of 0 is arbitrary constant c. Next, antiderivative of constant is kx plus c. You see, if you take the derivative of the right-hand side, the plus c disappears, and then kx becomes just k. You can check by taking the derivative. Next, addition rule. The derivative of sum is sum of the derivatives, right? Likewise, the antiderivative of sum is sum of the antiderivatives. Same goes for the coefficient rule. You can multiply by coefficient either before or after taking the derivative, so you can do the same thing for antiderivatives. Here's a bit of a warning here. Addition rule, yes, it works for addition. And then if you combine this coefficient rule as a value is -1, then it works for subtraction as well. So it works for addition and also for subtraction, but not for multiplication or division. And the reason is pretty simple, of course. If you take the derivative of product, then that's not the product of the derivatives, and derivative of quotient is not the quotient of the derivatives, so the same goes for antiderivatives. Okay, those are trivial rules. Now we need some real rules. The power rule. If you take the derivative of a certain function, say what's the derivative computation? Multiply by power and subtract 1 from the power. That's the computation, isn't it? That's how you do the derivative computation. Antiderivative computation, we go precisely backward. Add 1 and then divide. We used to multiply by power and subtract 1 to the power. Here, add 1 to the power and divide by the power. Precisely backward. The reason is obvious. Start from the right hand side and take the derivative. You'll see k plus 1 is multiplied and collide with this and they disappear. Subtract 1 from the power, we get k power. Yeah, that's the integrand. And plus c, of course, will disappear. There's an exception though. If k is -1, then we have denominator 0 here, so it doesn't make any sense. In that case, we have the second rule. You have a log function. You see, the derivative of log is 1 over x, or in other words, x to the -1st power. Why do we have this absolute value sign? That's because inside of a logarithm is always positive. Here, x can be either greater than 0 or less than 0. Is it equal to 0, then we have a problem because we have 0 in denominator. But it's okay either way. If you have just log of x, then we only need positive, no negative. So if you take absolute value, then everything looks good. Now, the easiest of the bunch, the natural exponential functions stay the same if you take the derivative. So if you take antiderivative, again, the same. So power rule, log rule, and exponential rule. Remember those, and let's begin some exercises. Ready? Okay, here we go. First problem. Let's calculate antiderivative of this. So we want the antiderivative of x to the 3rd power. How do I do that? 1/4 x to the 4th power. Did I do this right? Add 1 to the power, so 4, and then divide. We use this first rule. Next, let's take antiderivative of this. 3 was there before, so no problem there. And then 1/3 x to the 3rd power. add 1, and divide. And 3 was there before, so 3 1/3 will cancel each other out and they disappear, and you can write it as extra third power, and that's fine. But right now, I'd rather have all those separated. Final term was the antiderivative here, 1/2 x squared. That's easy, right? Add 1 to the power and divide. And then we have arbitrary constant c plus c. And if you want to do some simplification, go ahead. You can simplify this one, and that's it. So what did you do? We used the first rule, the power rule, over and over again. Simple enough. By the way, that's the answer key. Yeah, same thing. Next. Okay, let's find this calculation. And this is a power function, looks good. This one here, that's gonna need a little bit of work. We didn't learn any rule associated to multiplication. So let's simplify that. How can I simplify that? 2x to what power? First power, and then the radical, 1/2 power. So they become 3/2 power. So this one blue stay the same, and this one red, I change it into power form like this. And then finally this one green will stay the same, and I didn't apply any of the antiderivative rule yet. And that's why this integral notation and dx still there. Now let's apply the antiderivative rule here, especially the first one. Okay, 5 was there before, and then we have to add 1 to the power and divide. That corresponds to this blue term. Make sense? Next, 2 was there before, add 1 to the power, 5/2, and then divide. The second term, red. Make sense? 2 was there before, add 1 to the power, and divide. Dividing, so I took reciprocal. Finally, exponential stay the same. And then plus c. All good? Green? No, not yet. This and that. This and that. Are they the same? No, not really. This is e to the x. This is e to the 4 power. There's no x in there. So this is not an exponential function. This is just a constant. So you have to use the constant rule, you see? E to the 4 power times x. This thing times x. And you can easily check. If you take the derivative of this, you just get a coefficient, or you get end up with 0 power, so you just get a coefficient, e to the 4th power. That's this. Don't be fooled by e to the 4th power or e to the whatever power, square root of 17 power or whatever. It's a constant, so regard it as a constant. And then, as usual, we have plus c in the end. Let's see, we have some more problems here, but time's running out, so let's stop here and let's resume. We did some exercises, especially on the power rule multiple times, and we're going to come back and do more.